Okay, let's begin.
Sure. Okay. Let me share my screen.
Okay, our next speaker is Samuel Sanchez from Math Science Institute in India, and he's going to talk about aspects of cosmology in Palatini gravity. So I'll send you a reminder when 5 minutes are left.
Sure, thanks. Can you see my cursor?
Yes.
Okay. So yeah, hi everyone. Thanks for inviting me to present my research at this seminar. I am a postdoctoral fellow at the Institute of Mathematical Sciences in Chennai, but I'm actually finishing my time here, and yeah, next week I'm moving to IAP in France. And in this talk, I will mainly go over the results of these 3 papers. And I would like to advertise specifically these 2 on top with my collaborators, Alex Karam, Diraj Hasra, and Jose Terente. This one we wrote a few months ago, and the first one actually just came out today in the archive. And yeah, they are related to the dark energy and the scalar-induced gravitational waves part of my talk. Okay, so this is the outline of my talk. I will first give an introduction to Palatini FFR gravity, and then I will go over inflation, quintessence, and scalar-induced gravitational waves in the context of Palatini modified gravity. I will show how considering r plus r squared Palatini gravity in inflation is helpful from the model building point of view. I will show how you can reconcile potentials that are discarded by the data, bring them back in agreement with the data. Then I will show how it's also helpful in reducing tensions between recent data sets, namely DESI combined with CMB and supernova observations. And finally, I will talk about possible observational imprints of modified gravity, specifically in the scalar-induced gravitational wave spectrum during a period of radiation domination. And then I will conclude. Okay, so I'm going to talk mainly about modified gravity. So first, I should motivate why I will talk about modified gravity. So first, I will say a few words about lambda CDM, which is a 6-parameter model. These 6 parameters are the amplitudes and the tilt of a nearly scale invariant power spectrum for the initial conditions of the universe. And then the other 4 parameters are related to background quantities, namely the whole dark matter density parameter, the baryonic matter density parameter, the reionization depth, and the angle to the horizon after combination. And this model is in agreement with a wide range of observations. For example, here on top, I'm showing distance modulus for lambda CDM in the case of a universe completely filled with dark matter in dashed, and for a universe filled with around 70% dark energy and around 30% matter in full. And as you can see, it fits the data much better. Here on the bottom left, I'm showing the famous TT power spectrum of the CMB. Again, in blue is the theoretical prediction for these parameters that I'm showing here. And in red are the observations, and this is in great agreement. And top left is a rotation curve, basically the velocity of the stars or dust as a function of the distance to the center of the galaxy, which provides evidence for the existence of dark matter. And yeah, so in lambda CDM, basically most observations sort of agree on these rough values for the density parameter of dark energy. It's around 70%. Whole dark matter is around 26%, and 5% is corresponding to baryonic dark matter. So actually 95% of the content of the universe, although we know how much there is, we don't know the nature of it. Furthermore, when you start combining different data sets, considering lambda CDM, you start to see tensions between these different data sets. So maybe modified gravity could help us with both these things, both with easing the tensions or helping us understand better the nature of dark energy. Okay, so when considering modifications to gravity, perhaps the simplest possible modification is taking your Einstein-Hilbert action and just considering a function of the scalar. And I will also consider it to be a function of the field because I will be interested in non-minimal couplings between the field and gravity. But as soon as you consider modifications to gravity, then the formalism of the theory of gravity becomes relevant because they lead to different dynamics and predictions. So let's start first with the metric formalism, which is the most widely used, in which the connection is fixed to be the Levi-Civita connections. So you have your Ricci scalar, which you obtain by contracting with a metric the Ricci tensor, and the Ricci tensor is written in terms of the Levi-Civita connection. You can then vary the action with respect to the metric, and you find modified Freeman equations. So for example, if you look at the first one, you find basically the Freeman equation where the density is modulated by capital F, where capital F is the derivative of the function you start with respect to the Ricci scalar. And you also have additional terms which basically depend on time derivatives of this capital F. And what is capital F? If you compute the trace of the metric field equations, you find that it's dynamically related to the energy momentum tensor, to the trace of the energy momentum tensor. Okay, so now let's go to the Palatini formalism, which is the main focus of my talk. In this formalism, the Ricci tensor is a function of a general connection, a priori independent from the metric. So you have to vary the action both with respect to the metric and with respect to the connection. The variation with respect to the connection gives you that actually this a priori independent connection is the Levi-Civita connection plus this correction term here on the right-hand side, which depends on derivatives of, again, capital F. Capital F is still the same. It's the derivative of small f with respect to the Ricci scalar. However, if furthermore, more than however, if you again take the trace of the metric field equation, you find that capital F is now algebraically related to the trace of the energy momentum tensor. So for example, for F equals r plus r squared, Starobinsky gravity, you find an expression that mirrors GR. So that's already one big difference. Capital F is now algebraically related versus the metric formalism where it's dynamically related. But that's not all. Also, if you take the variation of the action with respect to the metric, you get basically the same equations as before, but you also get additional terms. These two terms that go like 1 over f squared are new. So both f, the fractional dependence of f on the matter content is different, and also the Freeman equations are different. So you get different dynamics. Okay, so that was the intro for what is f of r gravity and how the Palatini and the metric formalisms are different. Now let's move on to inflation. Inflation is a period of exponential expansion in the early universe, which solves the horizon and flatness problems, and which provides a mechanism for the production of the perturbations that source structure in the universe. And even the simplest models, like this one I'm showing here with an Einstein-Hilbert term, canonical kinetic term with a potential in the slow roll approximation, already give predictions that are in very good agreement with the CMB data. Here I'm showing the famous tensor to scalar ratio versus NS plot from Planck. You should note that this plot is dated. The bound on the tensor to scalar ratio is now lower, is 0.036. And there's also new data sets like ACT that are in tension with the CMB, sorry, with the Planck data. But for my current purposes, this plot is enough, because what I want to say is basically that both R-squared inflation in the metric formalism corresponding to this green line, and alpha attractors corresponding to this yellow surface. By the way, by changing alpha, you can go down in R. So both of them lie at the sweet spot of the Planck data. And what they have in common is that they feature a plateau in the potential. So concave potentials with a plateau are observationally favored. That's what I'm trying to say here. Okay, so now let's look at the model we considered in the paper. So we have an action with a non-minimal coupling between the inflaton and the Ricci scalar, and we also have an R-squared term. You can go to the Einstein frame by taking a conformal transformation where the gravitational sector is Einstein-Hilbert again. You have a canonical kinetic term after a field redefinition. You get a new higher order kinetic term, which during slow roll is completely negligible. And most importantly, you get this modification in the potential. So we considered this for different models, for example, an exponential potential or chaotic power law inflation. They're both ruled out by the data. And for both, and for many other potentials, which satisfy the following happens. So if you look at the denominator for large negative field values, this term on the right becomes much larger than this one. The initial potential cancels out, and you're left with a constant. So effectively, the addition of the R-squared term in the Palatini formalism induces a plateau in the inflationary potential, which, as I just said before, is observationally favored. And we need alpha to be larger than 10 to the 7, that's the lower bound, to satisfy the tensor to scalar ratio bound. And here I'm showing how this plateau is generated. On the left is the Jordan frame potential, just an exponential. And on the right is the Einstein frame potential with the plateau. And this is the expression for the potential on the Einstein frame. We also did some numerical work on this. We solved the dynamics at the Barkhan level in modified gravity in the Jordan frame. And we compare the inflationary predictions with these constraints from Planck on the amplitude and tilt of the power spectrum, on the running of the scalar spectral index, and on the tensor to scalar ratio. And this is a slice of parameter space. Kappa is the slope of the exponential here. Xi is the non-minimal coupling, and in yellow is the available region in parameter space. So for example, for some fairly natural values of kappa, 0.3, and the non-minimal coupling, 10 to the minus 2, alpha needs to be large, 10 to the 11, and we get predictions compatible with Planck. So again, considering r plus r squared generates a plateau, which is observationally favored and can rescue many potentials. Okay, moving on to the next part. Now we'll discuss how modified gravity can help us reduce tensions between different data sets, namely, as you probably know, between DESI and CMB data. This is from the DESI paper, these two figures. These are some marginalized posteriors with the density parameter of matter and the Hubble parameter, also with the sun horizon at the drag epoch. And this is for lambda CDM. As you can see, the CMB contour is in tension with the DESI. CMB is in purple and DESI is in blue. And one way to reduce the tension that has been widely explored in the literature in recent months and years is by considering dynamical dark energy, different models of dynamical dark energy. And this is the model we considered. We have a quintessence model with a canonical kinetic term. We have an exponential potential, and it's non-minimally coupled to gravity. I will not show the field equations again, because I mainly want to focus on the dynamical systems aspect. So basically, if you rewrite your quantities in this way, x1 and x2 are basically the density parameter of the field. x3 is basically the density parameter of radiation, and x4 is the field excursion, with the density parameter of matter having this constrained form. Then you can write your field equations in this closed form, where beta and epsilon are very complex functions of x1 through x4, so I will not show them. But the point is that we solved analytically we obtained the attractors and the fixed points of this dynamical system. And we found a couple of interesting consequences. The first one is that we find a late time stable de Sitter attractor, which always exists as long as epsilon, psi, the non-minimal coupling constant, is negative, no matter the value the slope of the exponential takes. This is in contrast to the minimally coupled case, where lambda, remember, okay, so before the slope was kappa, now we're calling it lambda, sorry for that. But in the minimally coupled case, to have acceleration, you need lambda smaller than square root of 2. And this constraint is relaxed when including a non-minimal coupling. So that's the first thing. The second one is that the coordinates in phase space for the fixed points are equal for both the Palatini and the metric formalism, which I'm showing here in red. Although, of course, the dynamics, as I already explained in the beginning of my talk, and as evidenced by these two pictures, the dynamics are different. Okay, so we numerically solved this dynamical system and fitted it to the data. What data? So we took the compressed CMB likelihoods consisting on the shift parameters and the density parameter of baryonic matter. We also took the DESI BAO data and the DES year 5 supernova sample. And here in this table, I'm showing the summary of our analysis. This is for the best fit parameters of, so in this case, Psi-Phi CDM, I'm referring to Psi-Phi CDM as my non-minimally coupled model. Phi CDM is the minimally coupled model. And I'm showing the improvement in fit with chi-squared. And I'm also showing the evidence with the base factor with respect to lambda CDM. the improvement in fit of the non-minimally coupled model with respect to lambda CDM is almost -15, and of the minimally coupled model is almost -10. And one of our main results is that the non-minimally coupled model is strongly favored by the data. We get that the log of the base factor is larger than 5. And where is this improvement in fit coming from? So here I'm showing some residuals for the different BAO distances. This is the comoving distance, Hubble distance, and isotropic BAO distance. With respect to lambda CDM, which we take as our fiducial model, notice that these are fractions. So lambda CDM corresponds to unity. In blue is the non-minimally coupled model, and in orange is the minimally coupled model, right? The dots with the error bars are the data. And we find that the improvement in fit is mainly driven by these two points in the Hubble distance. I am showing here some more residuals, and now it's for the distance modulus, and notice is a difference. So lambda CDM corresponds to 0. We binned the data, the supernova data, only for visualization purposes. Of course, for the numerical analysis, you have to take into account the raw data. And yeah, we find that both models feature this crossover with respect to lambda CDM and are able to fit both the low redshift supernova and the high redshift supernova better than lambda CDM. Okay, so that was how good the model does and why. Here, I'm showing some results from Monte Carlo simulation that we did using IMSc. In blue is the non-minimally coupled model, in orange is the minimally coupled model, and in green is lambda CDM. And there's a few important things coming from this plot. First of all, psi, the non-minimal coupling constant, sorry, we find that it's smaller than 0, so non-zero at more than 2 sigma. Not quite 3 sigma, but more than 2 sigma. That's the first point. The second point has to do with lambda, the slope of the exponential. For the minimal coupling case, we find that it's smaller than square root of 2 in agreement with the phase space analysis. However, when you include the non-minimal coupling, lambda, so this constraint is relaxed and lambda can be larger, as is shown here, which nicely agrees with our analytical estimate, well, calculations. Okay, and finally, we also computed the, or obtained more than computed, the functional posterior for the effective dark energy or quintessence barotropic parameter. In red, it's the best fit, and in blue are the different confidence level contours. So we find a phantom crossing at more than 2 sigma, not quite 3, but more than 2 sigma. Again, in agreement with the fact that psi is different than 0 at more than 2 sigma, but less than 3. Okay, and okay, something that I just realized I didn't include is that we also repeated the analysis in the metric formalism, and we find marginally better fit in the Palatini formalism than in the metric formalism. I think the total improvement in chi-squared is like 13.4 or something in the metric formalism. There's a 1 difference in chi-squared. All right, so now let's continue to the last part of my talk, where I will emphasize and try to make the point that upcoming gravitational wave experiments may probe the modifications to gravity and the formalism of gravity itself. But to talk about scalar-induced gravitational waves, I have to take a step back and talk a little bit about perturbation theory. So as you know, the universe is very homogeneous and isotropic on large scales. However, there is structure living on top of that homogeneity. And the correct language to describe this structure is cosmological perturbation theory, where you separate every quantity, like the metric or the energy momentum tensor, in a background quantity that only depends on time and on a space-dependent perturbation. So, for example, this is the most general perturbed FRW metric, where A, B, and C are perturbations, and each of them is expanded in a power series like this. Now, in cosmology, we are mainly interested in first or second order perturbations at most. So this series is typically truncated above 2. And the main point of this slide is that at any given order, different kinds of perturbations, meaning scalar, vector, or tensor perturbations, do not mix. So for example, here I'm showing at first order the equation of motion for the gravitational potential and for the gravitational waves, and as you can see, they are decoupled. However, when you go to higher orders, still at the same order, different kinds of perturbations don't mix, but you can have mixing with different kinds of perturbations from lower orders. So, for example, you can have second order tensor modes coupled to first order scalar perturbations. And that's what scalar-induced gravitational waves are. This is their evolution equation of motion in GR, where the left-hand side is basically the same as in first order, but on the right-hand side, you have a source term, which depends on the first order scalar perturbations. And after some work, you can calculate their power spectrum, which is basically a double integral in momentum variables, V and U. And then you also have this term here, which depends on the polarization of the gravitational waves. You have a kernel function that encodes the subhorizon late time evolution. And most importantly, you have basically the square of the primordial power spectrum coming from inflation. But okay, actually the observationally relevant quantity is the density spectrum of gravitational waves, which is related in this simple way to the power spectrum. And as an example, I took this figure from this paper by Inomata and Nakama, where they consider this expression for the primordial power spectrum. And in this figure here, okay, different colors are for different parameters, but for example, you can focus on the blue lines. In the dashed line, you have the scalar power spectrum, and in full, you have the associated density spectrum of the scalar-induced gravitational waves. And why is this interesting and relevant? Because we have all these gravitational wave experiments coming up in the coming future, like LISA, DESIGO, Einstein telescope in the high frequency range, and all the pulsar timing array experiments in the nanohertz frequency range. And although the primordial power spectrum on CMB scales has been measured with an amplitude of around 10 to the minus 9, of course, given that power spectrum, you would get an amplitude here of 10 to the minus 18 or something, which is tiny. But the thing is that at smaller scales, the power spectrum is not constrained, so it could be boosted. And if so, it could lead to primordial black holes. And if so, it would also inevitably lead to the generation of scalar-induced gravitational waves. So if we would be able to measure a signal like this, it would tell us a lot of information about the inflationary potential at smaller scales than the CMB. But again, the point I'm trying to make is that also these experiments will be sensitive to modifications to GR. Okay, so we want to do scalar-induced gravitational waves in Palatini F of R gravity. So we want to go to second order in perturbation theory. In order to go to second order, we first have to go to first order. And these are the Einstein equations to first order in the perturbations. I will not go into any detail here. I just wanted to show them. And this is one of the main results of the paper. This is the equation of motion for the scalar-induced gravitational waves. It takes a similar form than GR. On the left-hand side, you have this modified Hubble parameter. And on the right-hand side, you still have a source given by this expression here, where the first line is GR, but now you get all these additional terms, which depend on the perturbations of capital F, which again depends on the energy momentum tensor. But of course, if you want to obtain a specific spectrum, you have to fix your F function. And the choice we took was one of the simplest and better motivated. Again, Stravinsky gravity, R plus R squared, during a period of radiation domination with barotropic parameter of the universe equals to 1/3. Now, if you go back to the trace equation in the Palatini formalism, you'll find that the right-hand side actually only depends on the subdominant matter component present in the universe, because the trace of radiation fluid, of the energy momentum tensor of a radiation fluid is 0. And I'm showing this equation here to motivate what I'm about to explain. Basically, F is a function that appears everywhere in the equations, and it's given by 1, which corresponds to GR plus alpha, the density of matter over m Planck to the 4. And this is a tiny number, which motivated us to take a perturbative approach to the modifications of gravity. So we separate every quantity, like this field, in its GR part plus a modified gravity part, where the coupling constant is equal to alpha times the energy density of matter at present over m Planck to the 4, which is equal to roughly 10 to the power of minus 121 times alpha. So alpha could be huge, like 10 to the 67, and still you're fine in this perturbative expansion. Okay, so we expanded every quantity like that, and in particular the kernel, and we found that the modified gravity contribution to the kernel is proportional to the GR contribution times alpha, the coupling constant of R squared, times the temperature of reheating squared. And here I'm showing the results of some numerical simulations. In blue is the kernel squared in GR, and in orange is the contribution from the modified gravity. Okay, so this is another of the main results. We took the same power spectrum that I showed before, the log normal function, and we obtained that the spectrum of scalar-induced gravitational waves in R plus R squared Palatini gravity is a scale-independent amplification of GR. GR is in blue, and orange is modified gravity. And while we were writing the paper, some other group, Kugaraja et al., released basically the same calculation, but in the metric formalism. And what they get is that the modified gravity spectrum is actually suppressed at low frequency with respect to GR. So of course, you have that the prediction from modified gravity is different from GR, but also different formalisms give you different predictions. And here I'm showing a few different example spectra for a broken power law power spectrum, just to emphasize that these experiments may be sensitive to these modifications to GR. Which brings me to my conclusions. Regarding inflation, I hope I convinced you that R plus R squared is useful for inflationary model building. We were able to rescue discarded potentials like the exponential potential or chaotic power law inflation. Regarding the late universe, we found that the DESI data in combination with CMB and DESI-R5 data provides strong evidence for a non-minimal coupling in quintessence and also for a phantom crossing in the barotropic parameter of dark energy. And finally, we developed a general formalism for the production of